So now what are we going to learn? What are we going to learn? Okay, we're going to learn a few things. Okay, what are we going to learn? Okay, first of all, okay, how to do this in Mathematica. Okay, how to do this in Mathematica, and some of you in Python with some kind of library like scikit learn and so flow. Okay. Now you could do this in Python from scratch as well, but you know I don't recommend that. Okay, so you learn how to do this. Okay, in Mathematica, right? You will, well, how to do this? How to formulate the problem. Now I've shown you, for example, I've shown you regression. Versus, I haven't shown you classification. Okay, so right, or something like binary versus multi-class classification, etc. Right? So we learn how to formulate problem. Okay, learn this, learn that, right? Okay, what else you do? You learn how to, well, maybe I should put this under here. How to prepare data set. I, E, X, I, Y, I, here. Right? And you would also learn types of, these are called model. Okay? So this is basically a set of models. This is a set of models. Okay? Types of models. There are two types that we will learn. Okay? One is called neural network family or artificial, okay, as opposed to brain, i.e. biological neural network, animal brain. Okay, you learn this in tree-based method, many of them, and maybe something else. Maybe. Okay, yeah. Right? Okay, so in note, in a high level specification, Mathematica will choose model automatically. Okay, so even before you learn different types of models, okay. Right? Okay. Now, well, first of all, how do you do this? And so there are two things: how to prepare the data. B, how to set up the model. Okay. Now I'm going to use the word for the first time. Train the model. So train the model is also like your mom. Okay. So it's like setting up supervised learning environment. Okay. The machine does the learning. You do the training. Okay. You set up the environment where something is right or wrong, and you evaluate whether it's right or wrong. Okay. But the one that learns the right from wrong, that's the machine. Okay. When you use machine learning model, you are not learning. You are training the model to learn. You train the machine to learn. Okay. Just like when you're teaching your child to identify apples from orange, you're not learning apples from oranges. You know that. You're teaching a child to identify apple versus orange. In this case, you will be teaching the computer to learn Y, the right Y from the wrong Y, given X. Okay, but you know what the right Y is because you have the data. You have it in front of you. Okay. So how to spell, okay. And then, by the way, finally, now, because how to evaluate the performance, i.e. how accuracy of your training. Okay, so these three things you learn how to do, and you would be able to do it with Mathematica. So that again, for those of you who are going into health science or sustainability or smart city, we have all kinds of problems to do there. Okay, so you can leave a lot of detail for Mathematica to do. So, okay, so you learn this. Okay, now before we get to that, let's go to, in theory you should learn this first, right? But we can do everything simultaneously. Now, if this were a proper machine learning class, how do you think I'm going to teach this? I'm actually going to start here. Okay, I'm actually going to start here. Okay. But, and then it should go like this one. Okay, it should go like this, right? Yeah, this is how I would teach a machine learning class. I would teach the models. I would say, how do you evaluate, how do you formulate the problem, then how do you actually do it? Okay. But because this is, I guess your first class, I want to show you how this is done. So maybe I can start here. Okay, I can start here. Okay, let me show you how it looks like. Okay, so this you would see how the whole process is done. Then once you get more insight into this, you still will be doing this, but you will do a better job. Okay, this time you just do sort of like a baby toy problem. Okay, so let's do a toy problem. Okay, so this is my toy problem. Your toy problem as well. Okay, again, this is going to example data, right? Statistics. Now this is as silly as it gets, right? Female heights and weights. So what does it mean? It has two things, right? It has two columns. What's the columns? Height and weight, right? And so let's enter, right? So description, female height and weight. Columns heading, height and weight. Okay. Length, how many data point? 15, right? Now, so I'm gonna call this. By the way, this I two step. I call it. I load the data. Call it data FHW, female height and weight. And then I find out the length, 15. So that means 15 data point. Now, this is data point number 1, right? Now, if I want data point number 15, I can go -1, right? Because that's the last one. So the last person is, right? Why is the height 72 and the weight 160? That's kind of weird. I thought the weight would come first. I think this is a weight, this is a height. Okay? I don't know why. Column headings. Oh, I think this is alphabetical. Okay, sorry. Yeah, this is alphabetical, but in reality, I think this is the weight, this is the height. Now, how can we check? Well, just look at this list plot, right? Okay. Now, this turns out to be an artificially nice data set. Yeah, the person who weighs 64, I think this is oh no, I think I'm sorry, my bad. I think this is height, but this is in inches, right? Yeah. Okay, I'm sorry. So this is 72 inches, and this is weight is 164 pounds. Okay, 164 pounds. So the person who is, so there's a very clear correlation, right, between the person's height and person's weight. Now, if you want to be, precise about it, you can notice a little curve here. So it's not quite a straight line. Yeah, but for all practical purpose, this is a very clean data. It's a lot nicer than the data that we saw earlier, right? So how would I do this? First of all, how would I set? So I have this is my height, my x, right? What's my x? My x is the first column, right? So this is my x, okay? I'm just gonna write here x, okay? Now, it turns out that x is a scalar, meaning only just one value. So given the height, now I think this is predicting the weight from the height. So x or x is the height in inches. Okay. Y is weight in pounds. Okay. So it's a second column. Right? Now, watch this. I want to create a prediction problem. Now, the prediction, to set up the data, the prediction does this. Prediction. Okay, go to F1. Oops, go to internet. Type in the internet. Okay. The prediction function, okay, can be set up in two ways. Okay. Oops. Right. You guys see this? A little bit bigger. So this is the input. This is the output. Okay. So if I have this, I can create something called my prediction. Okay. Well, first of all, let's set the data. The data has to be in the form x to y, right? So if I put something like x to y. Okay, simply that, right? Set of x given point to y. That's all I need to do. Now, so that's it. You're done. You're done. So just to show you a very baby example how to prepare data set. Okay. How do we do that? You basically do set of x point to y. Okay. Or alternatively, you can do this as well. You can set x I point to y I. Okay, you can do this. In other words, you can say, okay, this other x points to y, or, okay, and this is a function called thread. Thread is sort of like a now I'll show you what the thread does. See that thread is a very nice function for data handling. So basically, it's a list point to a list of x point to list of y. Thread is sort of like it comes from in sewing. You know, when you take a needles and a thread, you put this thing through there. Well, it turns from list point to list into a list of item point to item. So you see that 58 points to 15, 115. 59 points to 117. Okay, so both of this work. Okay, so I'm going to create a model. Okay? I'm going to create a model. How to set up and train the model? Well, it's very easy. Okay, it's very easy. You just say my model is equal to, okay, predict, and then you put in there. Okay. See if this works. Okay, so let's say my model is equal to predict x y. See if this works. Okay. Actually, when you go to predict, okay, this is my note, we'll select the model for you. Well, actually, I should change the word to method. The model method. Okay. When you go to here, you would see that in option, let me just show you real quick, okay? This one, method. Yeah, see? So this, again, this is a top level, simple. In life, there's this guy called decision tree. This thing called gradient boosting tree, gradient boosted trees, okay? Linear regression, nearest neighbor, neural network, random forest. Gaussian process, I may cover, I may not. But anyway, 1, 2, 3, 4, 5, 6, 7. These are as basic as they come. Because they are basic as they come, it's very cheap, meaning computational. Okay? When you specify predict, all it does is try the simplest one. In fact, you can specify decision tree, you can specify this, you can say something like, okay, let me show you. Can I do this? Again, this method, okay, method, decision tree. Okay, if I did this, it's gonna go through the data, okay. You know what the computer was doing was basically walking down the descending the hill, the gradient descent. Now look, what you get is a function. Okay, so basically what we saw before is y is equal to function of x, but this is hidden. Okay, because it could be complicated. So it doesn't have A and B or beta coefficient. But it says that input type is numerical. Notice, method, decision tree. Method is decision tree. Number training sample 15. So that's your information. Now, this is because you specify to decision tree. If you don't leave it, if you don't specify, you leave it as automatic. Yeah, same thing. You can leave it as automatic, or you can just omit it altogether. You know, smart enough to understand. It's gonna go through a whole bunch of them, all 7 of them, I think. Okay, and find out the one that's best. It turns out the one that's best is linear regression. Okay, it's linear regression. Well, no surprise, because well, it's not even this. It's even simpler, right? The data set. Look. Okay. Now, so that's it. So that's my point number 2. How to set up and train the model. You just do this. How to evaluate the performance. Now you can do a few things. You can do what I did before, right here, right? Which is to find the error and sum them. Okay. But in machine learning, there's gonna be more than one way of measuring the error. Look, this way, right? What did I do? I take the height, square them, add them all together, take an average, take a square root. But what if I don't want to take the square? I want to take the absolute value and take the average. It's called mean absolute deviation. So basically, because there's so many ways of assessing the performance, there's a function that creates another object called performance measurement. Okay? Actually, let me go with the note I prepared. So this is my predictor. Get my predictor, right? It's the same thing, okay? For some reason, right? Okay. Now, for this model, I create a predictor measurement that gives you the function and the data. Okay, just do this. Okay, just create it. Just create it. Okay. Now, this performance measurement object has many things like report or so. Let's do that. It has many things, right? It has root mean square error. See that? I think R square is there. Standard deviation, right? Log likelihood. So it's not just root mean square error. It has so many things, right? So I'm just going to pick on the main one. The main one is this. And well, let me specify this to be linear regression, just to make sure that it looks like what we want. Method linear regression. Okay. See, because it's giving you a linear fit. Look what happened. See that? I don't know if you can see this. Let me blow it up a little bit. Remember I mentioned that it looks like there's a little curvature? Yeah, it looks like a linear line fits really well. But when you look at predicted value versus actual minus predicted, what happened here? For people who are short and for people who are long, for women who are short, women who are long, they tend to be heavier than your prediction, right? Heavier by 2 or 3 pounds, right? So that's pound. So for short and tall women, the model fits the line here, but the actual data show they're a bit heavier than that. But for people who are of average height, the model actually over predicts. So most people, for people who are average height, women are generally less heavy or lighter than the linear fit. Okay, so this line gets accentuated Okay, obviously, right? So this is 120, this is 110, right? So this is only 2 or 3, but when I plot in this, it looks exaggerated. This is called residual error plot. Okay, and this is good with so you can do R square, you can do all kind of stuff. Okay. So that we can do this, and I did another example here. This would be quickly. Let me just run through this very quickly. This is using free data. Okay, using free data. I think you can do this. You don't need that. Okay. So basically, if I go to here, right? Let's go to a website. Okay, and I put in the name of company, like say 3M. Okay, that's kind of nice. 3m.csv. If this is actually the name of the data file. Okay, this is actually the name of the data file. So, okay, so if I want to import just that, I can say my data is equal to import. See, that works still. We have attempted to premium database without providing. Please register for free. Oh, so apparently this one is not free. I think if you do a Google search, you'll be given a key. Yeah, I think this is for one-time access. I should have erased that. So anyway, so now I'm going to get this. So my company is like a table, okay? Except I have many company. I think this is Caterpillar, this is IBM, JP Morgan Chase, or something like that. Okay. So these are all the data, right? And it doesn't have just the price, it has the date, open, high, low, close, volume. So let's see the last one. M&M. Oops, sorry, not M&M. Okay. Let's say 1, 2. So I get the heading as well to 10. Okay, 10. Okay. So let's put that in the table form. There. So that's it. Date, open, high, low, close, volume, dividend. Date. Okay. Open, high, low, close. Okay. So this open means well, the price that it opens in the morning, the high it gets in the day, and this is so beginning, end, beginning, end. Now it looks a little bit funny that sometime, okay, this is the beginning, this is the end, right? So this should be the opening, but sometimes there's a kind of movement overnight. So this is not exactly the same as that, but that happens. Okay, so don't worry about it. Anyway, so this here is just indexing function that I create. Now, normally you wouldn't use this. You would use this thing called data set. And remind me after we come back from exam to talk about data set, because data set here is, well, let me make a note how to prepare data set. Now, notes in practice, instead of use just list, you might create data set object, okay? Which is in Python equivalent to pandas. Okay, so that's a note for those who have to take Python. Okay, so data set here is like a data frame in Python. Okay. In practice, you might do that, but here, you know. So anyway, so I can just show, you know, the various date. What I did was just I take adjusted close and I take this blah blah blah. I just make a company, right? And I just do a yeah. So basically, I'm just plotting the value here. Okay, it's not a big deal. Just the four companies. This is a histogram of price and so forth, right? My model, okay. Now, I happen to turn this into a time series. Don't worry about it. Okay. The only thing else and something else I do is that I separate what's called training and test. We'll go over in detail a little bit. Okay. Now, in regression, okay, fine point about setting up about A, preparing the data. Okay. Now this is another insight I want you to get. Again, the practical part will show you how to run it, and we'll have time to do that in your project. In linear regression, you pretty much use all the data. Okay? Use all the data. Okay, that's because if you look at it, okay, the linear line cannot fit everything. Okay, it cannot fit everything. There's going to be some error. Okay. Okay. As the model will kind of ignore noise. Okay. With machine learning, because the class of F is, let's say, powerful, okay, it can actually fit all the noises. In other words, instead of drawing a line here, okay, you can imagine that it draws a line here, right? So this, you should stop here. You should stop here. Okay, you should stop here. Because, yeah, this is good. This is perfect already. Okay, this is good. So let's put it again. Oops. Okay, so you get the perfect solution already. This is as good as it gets, because in machine learning, the model is so powerful, it might try to create a line that strings every single point together. So it's not just drawing a straight line, right? With linear regression, you use all the data and it fits this line. It fits this line, right? It ignores the noise. But you can get perfect fit. You can imagine there's like a square, a really fine-tuned, squiggly line that fits to all the data points. The point is that you don't want to do that, okay? Because it may be this particular sample that has this kind of error. The next sample may have the error this way. So what machine learning tends to do is to avoid overfitting. You kind of don't use all the data. Okay? In fact, separate them into training versus tested data. Okay? And let me put another note. In the future, you will also use validation. Okay? Right now, so that's what this thing does. Okay? Take drop. Okay? Take droplets is like this. If I take drop A, A, B, B, C, D, E, F, and I put in say 4. Yeah, it's gonna take the first 4 and drop the remaining. Okay, so if I take the length of the data and multiply by 8, floor, this is like round down, and I take drop. What it means is that it's gonna separate the data set. Okay, the data set, which is okay, 1080 days or 79 days. Okay, if I do this, okay, take drop, I'm gonna have 2 sets of data. I'm gonna separate the first 80% into the training data testing. In practice, you are going to use this thing to train the neural network or the machine learning model, and then you're going to report the result based on the unseen. So otherwise, this is known as AKA in sample versus out of or out sample. Validation, by the way, is considered in sample. We'll talk about it later. Okay, so that's it. So fine point about this. Now, how it's done, I just want me to show you quickly just how, so you don't have to worry about how this will be done in practice, because again, at the top level, at the most basic, okay, you haven't built any model, right? You just use the simple. So so in other words, from statistics class, you know how to do linear regression. With this, you are able to do a few more things. You are able to do decision tree, gradient boost, except, I haven't even told you what they are, okay? Again, this is not a machine learning class. A machine learning class, I would teach what they are first and then show them how you would use it. Here, it's sort of like the other way around, right? So I'm showing you how you would code it. But in reality, you have to understand how it works, because different models have different advantage. Okay, that's what makes professional data scientists and hacks, the differences between knowing what's happening. Okay, anybody can code this, but I want you to have this good thing. Now, so today, I really want to spend like half. No, actually, I wanted to spend an hour to talk about project, but I think half an hour should do. So I want to go into classification. So once again, you guys remember that, right? Regression versus classification, right? So regression, y is equal to number, okay? And then y
sorry to interrupt. Before we proceed to the next topic, is it okay to take a break a little bit for breaking the record?
Okay, okay. So when we come back to the break, we're gonna say y is equal to the number versus y is equal to category. Okay, okay. So again, this is what a linear regression problem looks like. I broke it down into steps you would take if you don't have the basic assumption that it's a line, but you have a more general concept of a function class. So we're trying to fit the data with a machine. That machine here is nothing more than machine collection of function Okay, something like that. Each with parameter beta subfunction, right? So beta is not the same, right? Beta function of that function. Okay. Learning algorithm that gradient descent the error value by to minimize Y model versus Y real. Okay? Okay? That's it. Right? So who's doing the learning? The algorithm. You are training. So that's why you, human, don't learn. You train the machine to learn. Okay? You don't do the learning yourself. Instead, you train the machine. Okay? Now, so what's the difference, right? Regression versus classification. So if I want to say height, y is equal to height, that's obviously a number, right? In fact, height belongs to what scale? I guarantee you that I'll be asking silly questions like, you know, what kind of scale does height belong to? What kind of scale does cat belong to? Okay. Now, so obviously, if y, okay, is from, okay, say real number line, okay, versus y from cat, dog. That's a very different things, right? Okay. Let me put on either side. So this is one. So this is regression. What's this? This is classification. Okay. Now let me make a side note. You know why it's called regression? You are, well, go back in history. A person that child height as adult regress to parents or population height. Depends on what different concept. Let's say okay. So sometimes you can have, you know, if you think about it, a tall person tend to have tall children, right? But in a way, it doesn't keep forever. It doesn't keep getting taller forever. It kind of regress to the tall parents, but not, you know, it doesn't keep getting taller and taller and taller and taller over the generation. So that's why the word comes from. Okay. Now classification. Side note. classification in biology, okay, the problem is identification. Okay, in other words, taxonomy. Okay, classification separates cats from dogs. Okay, and taxonomy identification tells you this animal equal to cat, not dog, or vice versa. Okay, so in this case, your classification problem is actually identification. The classification is done for you. So from cats and dogs, it's called label. Okay, so that's a side note, right? So you have labeled cats versus labeled dogs, and your classification problem is to look at a picture and say, is it a cat or a dog? Now this is different from your friend in biology or medical school, because in biology, classification is the original taxonomy. It's separating all cats from dogs. It's the labeling, right? Identification, when you see something and you say, is it a cat? Is it a dog? Is it cancer? Is it tumor? That's called identification. Okay. So anyway, just so you know. Okay. So this is your classification. Now, obviously, I don't know if it's obvious to you. Obviously, most function, mathematical, produces a number, right? Mathematical function produce numbers, not cat, right? Not cat. So there has, so in, now I'm gonna forget about biology now. So in classification, in ML classification by machine learning, you need something, another function, G, that maps numbers into category. Maps. Okay. Okay. Now, what is the easiest way? What is the simplest way? Think of the simplest case. Think of the simple. Okay. Okay. To say G, you want this is what you want, right? G of F of picture. Yeah, so you have a picture, right? And you have some kind of machine learning, okay, some kind of F. Now your machine learning is gonna do this. Yeah, this is what you want to do. But G in itself has to be a number, right? Because G is a function. So let's do this. Okay. Let's do this. Define catness as a Boolean. True or false. Okay? Let's do this. Now this is general, but next again, define catness. Step 1. Define catness as Boolean. There. Note. Step 2. By default, let's create a corresponding true, the same as 1. Okay? And false. Okay? Now this is kind of common sense, right? Most people do this, have no problem doing this, right? So to do this, so now you say something like G picture is equal to catness if catness equal to 1, i.e. true, say cat. If catness or else, now catness can only have 2 values. Okay, define catness. Let's define it as a Boolean level. Okay. 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 Now, G is equal to cat. I'm gonna call it Y. If Y is equal to 1, 0, catness not true. Say not cat. Else. Okay, where Y can only be 0, 1. Okay, let's do that. Let's do this. Okay, so let me make it big. So let's go. Okay, not true is the same thing as false. Say not cat. Okay, all right. Now, notice this only works what? This is called, because Boolean has 2 values, 1, 2. This is called binary classification. Okay, so cat, not cat. Okay. Now, life is not good, right? Life is not good, right? So Okay, this is step one. That's not good enough. What if you have cat, dog, or mouse? Okay. What if you have cat, dogs, or mouse? Now this is where it gets tricky. Okay, it gets tricky. Okay, you can do two things, two choices. You can either define y from 1, instead of 0, you get 0, 1, 2. Okay, 0, 1, 2. Where 0 implies cat, etc. Or you ask catness, dogness, mouseness. Ask 3 questions. So, or you define y1 for catness, y2 for dogness, y3, and each of them can only be okay. This is called multi-class classification. Now, sometimes you don't need to make the distinction. It's obvious what to do. So you have to name it. Multi-class classification. Okay, or multiple binary classifications. Okay. Yeah, right. Okay. So anyway, so this is the gist of it. Now, by the way, which one is a cleaner approach? To be honest with you, this is actually cleaner. Okay. Why is it cleaner? Oops. Define, because this you can do something like arithmetic, right? 2 is greater than 1, 1 is greater than 0. Why am I getting this stupid Microsoft? Oh, because it's stupid Bing thing. Yeah. Okay. Because when I do this, it sort of implies that mouse is bigger than dog or bigger than cat or something, which I don't want to do that. In other words, this looks ordinal scale. But you don't want ordinal scale, you want nominal scale. Okay. So this is cleaner. This is purely classification. But you need to do just just make sure only one of them gets to be 1. Okay, otherwise you have cat and dog nest. So this is it. So this is how, this is about, you can think of it as find point about formulation, right? So here, how to formulate the problem. Okay, regression versus classification. Right now, having done that, let's see what it looks like. What it looks like. Yeah, what it looks like. I'm gonna be very quick because we don't have a lot of time left. Okay, so I'm gonna go straight to this thing, which is what's called iris. Iris. Now, in reality, when you give Mathematica 3 classes, it does equivalently between this thing. Okay, so it hides the detail. But when you write in the model, for example, I'm writing the model for my consultancy project. I literally have to try both configuration because I don't know which one would use a better result, right? But from say Mathematica, I have this thing, 3 things called iris. There's a pitch, there's a classification, right? I don't know this iris data, right? There are three values, and let me just run real quick. Okay, you can follow the step. You can thread. You don't need to thread actually. So instead of building a model called predict, so predict for classification, Mathematica uses classify to build a model. Okay. That's supposed to be on top. For regression, Mathematical use predict. Okay, so keep that handy. Okay, so we built this thing called classifier iris. Now it's not going to give you sort of like a number. It's going to give you classification. So and we'll come back to this after the exam because you learn into detail. So this gives you a classifier. It actually gives you a method called logistic regression. Okay, we'll go over all this in detail. Number draining, and these are the classes: setosa, versicolor, and virginica. Okay, and similarly, I built a classifier measurement. Okay, I used to have a predictor measurement, right? I create a classifier measurement, and I can show you accuracy. But more importantly, these are the 2 things that you'll be looking at. It's called confusion matrix plot and confusion matrix plot and okay, there it is. I don't know why it's getting big. Okay, what it says is this. Okay, what it says is that this is actual. Again, you're comparing actual versus the model output, except you don't have value with value, you have classification. So actual, setosa, predicted, setosa, 50% of the time. Sorry, 50 cases. So actually, this is very good. So out of 50 setosa, perfect. Out of 50 versicolor, 1 is misclassified as virginica. Out of 50 virginica, 1 is classified as versicolor. If you will recall, I did use this data set for clustering example. And you will find that I think in the sheet that I sent in the line last week, it actually clustered these two together, Virginica and versicolor closer together. This is called ROC plot. This is not realistic. In life, you don't see this. In life, you see something like that. But we'll come back to the detail. Okay. I'm going to give you this so you can play with this as well. This is the concept that, you can do nonlinear regression. Again, this is not machine learning. This is statistics, right? This is a method, except in this case, it's nonlinear. Okay, I just want to skip this. But anyway, you can use Mathematica for this purpose as well. Okay, so I create some kind of data and I kind of fit. Now, the function here, nonlinear model, is called fit. I create a sample fit and that is the data. Okay, so this is my data. Okay, it's just like the previous example. I fit them with this. Now, these are called kernels. Okay, I happen to create a kernel. I don't know what 58 is. Oops, I screwed up something. Okay, I don't know. Anyway, so this is the line of best fit. This is artificial line. This is the line that the model created. The reason it's not the same, you know why? Because I didn't allow the fit model to have intercept. So it has to have a point 0, 0, right? When x is equal to 0, y has to be 0 because I don't allow for intercept. So even though theoretically the blue line is the best, okay, I artificially say I don't allow that. I don't allow that. I allow x, x1, x squared, x cubed, x fourth, x fifth. I don't allow intercept. So I get there. So it's still pretty good. But by the way, this is not machine learning. This is not linear regression. Okay? Logistic regression. Finally, this is the last thing I'm going to say. What it does is using this function, okay, exponential, well, basically just ignore all this. Just look at this. I like to show you how the function is created. But I'm just going to go to the last function. This is a final function. Right. Now, see this? This function turns a value of minus infinity to 0, plus infinity to 1, and anything in between into something like this. So this is what you would use here. Okay? So example of a model. This is logistic regression. Now, still not yet machine learning, but what logistic regression is, it turns y logistic function, so sigmoid function, turns high y into near 1. Hence, true. Okay, this logistic sigmoid also turns high negative, low or negative. Y into near 0. Hence, false. Also turns near y near 0 into 0.5 to indicate not sure. Okay, So this is how you can turn number. Remember that linear regression only gives you number, right? So you have this function that I show you here, 1 over 1 minus, so instead of x, this would be y. Y would be the value of the output from a regression. So you can think of y, okay, y as a value that express catness. The higher the value, the more likely it is a cat. The lower or the more negative the value, the less likely it is a cat. Okay, and if it's high, it goes to 1, true. So this is how, so this function, this logistic function is the G, it's this thing. It's this thing, kind of like, okay? So in other words, so you have G of some kind of machine learning, regression, some other function, okay? So you can think of this as a regression function, this as a logistic function, and together it's called logistic regression. And it gives you something that close to 1 for something that looks like a cat. Now, obviously, the picture, the input will not be numerical. We'll talk about that later. Okay, sample of a model. Classification. Okay. Come back. From midterm, learn real. Real. Okay. So, okay. Now, I want to give, okay, นัดครับเดี๋ยวเราหยุดเทปตรงนี้ดีไหมแล้วเรามาดิสคัสตรงโปรเจกต์พี่อยากจะให้ครึ่งชั่วโมงแต่นี้มันเหลือ10 นาทีแล้วแต่ว่าไม่เป็นไร
Okay, let me stop here.